Welcome back, everyone. You know how much we love to geek out here on the Deep Dive. And today we're diving into a concept that's really fundamental. I'm talking about the very core of how we think about, well, basically everything, whether you're coming at it from science or from, a more philosophical angle.
Yeah.
We're talking about mechanism.
Yeah. I mean, it's inescapable. If you're trying to grapple with the big questions, how do we explain why stuff happens the way it does? Well, you got to wrestle with this idea of a mechanism, all its little twists and turns.
So that's our mission today, right? We're going to dissect this idea of mechanism, specifically how it's been shaped and debated within the philosophy of science. Think of it like upgrading your philosophical toolbox, specifically for figuring out how different sciences build their whole picture of, well, reality, I guess you could say. And our roadmap for this journey, we're going to lean heavily on the Mechanisms in Science entry from the Stanford Encyclopedia of Philosophy, pretty much the go-to resource for this stuff.
And what's kind of wild right off the bat is when you look back at the history of mechanism, you see this double life it's led. On the one hand, it's been like this badge of honor, a way to celebrate the strength of scientific explanation, like picture the perfect clockwork universe, that kind of elegance. But then flip side, it's also been used as like this critique, right? To imply that maybe this view is too narrow, too simplistic to capture the real richness of reality.
For sure. Back in the 17th century, you had these heavy hitters, Descartes, Gassendi, Boyle, and they're pushing this mechanistic worldview. The whole thing hinged on the idea that matter is fundamentally the same stuff, and everything could be boiled down to local motion, stuff bumping into other stuff. Total break from the dominant Aristotelian ideas about formal and final causes.
Right. And then, fast forward to the 19th, 20th centuries, bam, mechanism is right in the thick of it, going head-to-head with these more holistic, vitalistic ways of explaining life.
It didn't stop there, though. Late 20th, early 21st century, along comes the so-called new mechanism. This wasn't just picking up where things left off. It was a whole reaction to, the reign of logical empiricism, which had basically dominated philosophy of science for ages.
Right. So logical empiricism was all about the formal structure of scientific theories. They didn't really get into the nitty-gritty of the content itself. But these new mechanists, they flipped the script. They put the spotlight on the actual practice of science. They wanted something more grounded, really focused on the material world.
So instead of starting with these airtight logical frameworks, they were saying, hold up, let's see what scientists are actually doing when they make discoveries, when they figure out how to explain things. It's a huge change in the method of philosophy itself.
Totally. And by looking so closely at the way science actually works, they hit this really key question. What the heck is a mechanism anyway?
Which brings us to the meat of our discussion today. How do you define this thing that seems so obvious on the surface, but then when you look closer, turns out to be so slippery? And right away, the Stanford entry points out something really important. There's not just one definition that everyone agrees on.
It depends on what you're trying to do, right? Are you coming at it from the perspective of epistemology, like how do we even learn about mechanisms? Or are you more into explanation? How do we use them to understand the world? Even looking at the history of science or the metaphysics behind it all, the stuff you focus on when you're talking about a mechanism might shift around.
The entry lays out some of those early influential definitions, like Glennon's, where it's all about complex systems, behavior emerging from parts interacting according to direct causal laws.
Yeah.
Or Machimer, Darden, and Craver, they focus on these entities and their activities and how they're organized to bring about regular changes.
And then, of course, you've got Woodward with the interventionist take.
Yeah.
He brings in this idea of invariant generalizations and how you can mess with different parts to understand the cause and effect relationships going on inside the mechanism. And Bechtel and Abrahamson, they come at it from a functional angle, a structure doing a specific job, working through the coordinated efforts of its parts.
So it's like all these different philosophers are circling around the same core idea, but they're each bringing their own questions, their own priorities to the table. The initial focus was on concrete parts and direct interactions, right? But then the later emphasis on stuff like intervention and function, that shows that people were starting to think more deeply about how we know about these underlying structures, how we use that knowledge, not just what they are in some abstract sense.
You got it. And this whole explosion of definitions, it wasn't a bad thing. It meant that philosophers were finally digging into the concept of mechanism with the same rigor that they had applied to ideas like law or cause. Before that, people threw the term around, but they didn't really stop to pick it apart philosophically.
So how did they start to find some common ground amidst all this diversity?
Well, Glennon and others, they put forward what's become a pretty widely accepted definition. We call it the minimal mechanism definition. They say a mechanism for a phenomenon consists of entities, or parts, whose activities and interactions are organized so as to be responsible for the phenomenon. It's a bit of a mouthful.
Okay, so let's unpack that minimal mechanism definition. What jumps out is what it doesn't include. Like, there's no mention of regularity. What's the significance of that?
That's huge. By leaving out regularity, they're saying you can have mechanisms that only work under super specific, maybe even unique circumstances. It's not always about these perfectly predictable clockwork outcomes. It's more flexible.
So a mechanism might be involved in something that happens once and never again, and it would still count as a mechanism.
Right. They're not bound to these, ironclad laws. Plus, there's no requirement for a specific function or goal, and it doesn't have to be perfectly modular like Woodward insisted. Real-world mechanisms, things can be pretty messy and interconnected.
So this definition is more inclusive. It zeroes in on those core ingredients. The entities themselves, what they're doing, their activities, how they relate to each other, their interactions, and how they're organized, and their role in making that specific phenomenon happen.
Exactly. And to make this more concrete, the Stanford entry gives us these visual ways to think about mechanisms. Really helpful.
Yeah, there are those two classic diagrams. Figure 1 shows a system at the top doing its thing, and then inside you see the parts, their organized activities, all leading up to that behavior. It's like a blueprint of how the whole thing is put together.
And figure 2 gives you another perspective. It's a mechanism as a process unfolding through time, like a chain reaction transforming inputs into outputs. Really handy for understanding how a phenomenon develops step by step. And as a real-world example, they show you figure 4, a climate mechanism.
Across all these different ways of visualizing it, what keeps popping up, they point out 5 key elements: the phenomenon itself, the parts of the mechanism, the activities those parts are up to, how they're organized, and then usually you've got different levels of organization involved. Let's start with the first one, the phenomenon.
The entry says it straight up, every mechanism is a mechanism for a phenomenon. Seems obvious, but it's super fundamental, sometimes called Glennon's law. You can't even start analyzing a mechanism without knowing exactly what it's supposed to be explaining.
So like the complex mechanism of photosynthesis, that's the mechanism of plants using light to make energy, right? The mechanism itself, its boundaries, they're defined by what's relevant to that specific phenomena.
Precisely. And phenomena, they define them as object involving occurrence, which sounds kind of jargony. Think of it like a ball rolling. Ball is the object, rolling is what's happening. It means some object or system is doing something, a process, an event, a state.
A muscle contracting, an ion channel opening, those are phenomena that scientists would try to explain using mechanisms.
Bingo.
And when we say a mechanism is responsible for a phenomenon, what does that really mean?
Depends a bit on the situation. It could mean the mechanism actually produces the phenomenon, especially when you're talking about a sequence of events through time. Or maybe it underlies the phenomenon. Could be, in a physical sense, made of smaller parts, or a causal sense, the process connecting inputs and outputs. It could also mean it's what maintains or controls the phenomenon.
Next up, the parts of a mechanism. It doesn't seem like it's as simple as just, part-whole relationships, is it?
Oh, way more to it than that. The basic stuff about parts and wholes mereology doesn't really capture the whole picture of how we use parts when we're talking about mechanisms. There are all these different angles. Some people focus on whether the parts are physically real, though defining what physical even means is a whole other philosophical rabbit hole. Others, they emphasize what each part does within the mechanism. That's how they define the parts.
The entry also talks about nearly decomposable components. So that's where the connections within a component are way stronger than those between different components.
Right. And they also talk about stricter rules. Like Glennon saying a part should be pretty robust, like it should exist in some way even outside of that specific mechanism.
That might be asking too much for some mechanisms, though, right? Like, if you think about fleeting biochemical reactions or even the mechanisms behind natural selection, it's not so clear what the parts are there, and you can't really isolate them so easily.
Good point.
Okay, so then we get to cause. How does the concept of cause work within a mechanism?
This is another area where philosophers, well, they love to debate. The entry breaks it down into four main camps. First, you've got the folks who focus on conserved quantities. Think like energy or momentum being transferred. That was a big name there. Second, the activity-based approach. Bogan and Mortimer are in that group. They're all about pinpointing those specific actions that make things happen without trying to reduce causation to one big idea.
And those actions, those activities are real things that happen. It's not just like a way of talking about them.
Right, they're trying to get at something more fundamental. Then you've got the counterfactual accounts, which often come with a manipulationist twist. Like, what happens if you change something? Woodward's big on that. And lastly, you've got the mechanistic accounts of causation. Glennon's a good example. It's like they're saying causation at one level is basically defined by the mechanisms going on at a lower level.
Sounds kind of circular, doesn't it?
It can be. And of course, each of these approaches comes with its own, baggage, criticisms, limitations, you name it. The conserved quantity folks, they run into trouble when they try to step outside of physics. The activity-based folks get criticized for not explaining what those fundamental activities really are. Counterfactual accounts, well, it gets really tricky to define those what-if scenarios in a rigorous way. And the mechanistic account, yeah, as you pointed out, it can get pretty circular because mechanisms, by their very nature, seem to involve causation.
It all mirrors those bigger debates in metaphysics about like the ultimate nature of cause. So let's move on to organization. What is it about the organization of those parts that makes a mechanism actually work instead of just being a jumble of components?
That's where organization comes in. It's about how the parts are arranged. And it's not just any old arrangement, right? It's got to be something specific that allows them to interact in certain ways. Together, they could do stuff that they could never do alone. Organization can be all sorts of things. Spatial arrangement, the order in which things happen, causal dependencies between components, hierarchical structures with different levels, and even like more abstract patterns of interaction.
The entry also talks about modular organization, right? That's where a mechanism is made up of these self-contained subparts. That seems pretty important for those counterfactual accounts of causation, where you're supposed to be able to tweak one module without messing up the others.
Spot on. Woodward, he's all about clean, localized interventions. Steele, he's got a slightly looser, more probabilistic version based on Simon's idea of nearly decomposable systems. The idea is that components within one subsystem, they interact way more strongly with each other than they do with stuff outside that subsystem.
Lastly, there's this concept of levels. How do different levels of organization play into our understanding of mechanisms?
Well, the mechanistic view of levels is totally different from these older ideas that were more about size or about everything being at one level. Here, levels are local. They're defined within a specific mechanism, a multi-level one, usually. Something's at a lower level if it's a part of something at a higher level, and its activities, what it does, contribute to the behavior you see at that higher level.
So it's a part-whole relationship, but it's defined by the causal connections within the mechanism. Craver puts it this way: an activity at a lower level that's a constituent part of the system's behavior at a higher level. Or you could think about it in terms of input and output. The lower-level components, they're the middlemen in the whole process.
And this whole idea of levels, it's essential for understanding how different models in biology, for instance, fit together. Like, how does the stuff we know about molecular genetics connect to Mendelian genetics, which is at a whole different level of organization? But even this mechanistic view of levels, it's got its critics, people who raise some good questions about whether it really holds up in the messy world of actual science.
Now, the entry spends some time clearing up what mechanisms are not. Seems pretty important given the long history of the term and all the different ways it's been used.
Absolutely. To start with, mechanisms don't have to be deterministic. They can involve probabilities, random events, that kind of thing. They're not limited to those simple push-pull interactions that the early mechanists were talking about. And this is a big one. Saying something is explained by a mechanism, that doesn't automatically mean you're a reductionist. Actually, the whole framework of mechanisms is often used to understand explanations that cross multiple levels of organization.
Yeah, and they're not just machines, right? Machines are designed to use mechanisms, but they're usually made for a specific purpose. Mechanisms themselves, they don't have to have some preordained goal. It's more about how the process than just a static arrangement of parts.
Totally. Plus, mechanisms aren't always these neat step-by-step processes. You can have feedback loops, cycles, all sorts of complex interactions going on, and they don't have to be confined to one specific location. The components of a mechanism can be spread out all over the place. And maybe most important for us philosophers, mechanisms aren't just metaphors or stories we tell ourselves. They're about real things, actual processes happening in the world. And one last thing, mechanisms aren't just sitting there in nature, neatly packaged with clear boundaries.
Yeah.
The boundaries, we draw those based on what's relevant to the specific phenomena we're looking at.
And then the entry gives us a handy list of things that are definitely not mechanisms. This is super helpful for getting a grip on the concept.
Right, like a rock, that's not a mechanism. Neither is a simple object that isn't actively doing anything. Correlational patterns, they might give you hints about what's going on, but they're not mechanisms themselves. And just a sequence of events or a spatial arrangement, if there's no causal connection, that's not a mechanism either. Things like inferences, logical arguments, mathematical stuff, laws of nature, taxonomic categories like the periodic table, those aren't mechanisms.
So now that we've got a much clearer picture of what mechanisms are, and just as importantly, what they're not, the big philosophical question is, why is this concept so central to how we understand scientific explanation?
The entry argues that it all boils down to this deep desire to understand why things happen, to get at the underlying causes and the processes that make things unfold, rather than just describing patterns or coming up with unifying theories that are neutral on the content itself.
Right. It's about the nuts and bolts, the nitty-gritty of how things actually work. And that's where those earlier models of explanation, like the covering law model or unificationist accounts, they kind of fall short. They were influential, for sure, but they don't really capture the way scientists actually explain things in the real world. They struggle to tell the difference between a real causal law and just some random pattern, or between making a prediction and offering a true explanation. They weren't focused enough on those concrete, causal, mechanistic structures that scientists are always trying to uncover.
Exactly. And just to avoid any confusion, it's super important to keep in mind the difference between the models we use to represent mechanisms and the actual mechanisms themselves out there in the world. Some philosophers, they really focus on the ontic mode, meaning those real structures in the world. Others, they're more into the representational mode, the way we convey information about those mechanisms through our models. Both are valuable, but you got to keep them straight.
The entry then gets into Salmon's distinction between, etiological and constitutive explanations. Can you break that down for us?
Sure thing. So etiological explanations, they're all about the history of an event. What caused what? Like, why did that window break? Because a ball hit it. That's etiological. Constitutive explanations, they go deeper. They're trying to explain the phenomenon by laying out the underlying mechanism, all those internal causal connections, like explaining the broken window by describing the physical properties of the ball and the glass, the forces involved, that kind of thing. The new mechanism folks, they've been mostly concerned with this constitutive side of things.
And the entry makes this point, which I thought was interesting. It's not like the mechanistic view says that phenomenal laws, those that just describe regularities without mechanisms, have no explanatory power. They can be useful, right?
Yeah.
Especially for etiological explanations, figuring out what caused what, even if they don't dig into the how at a lower level.
Right, but when we're talking constitutive explanations, how something at one level is produced by the organization and actions of its parts at a lower level, those phenomenal laws, they just tell you what happens. They don't say why or how in terms of the mechanism.
Which leads us straight to those limitations of the covering law model when you try to apply it to constitutive explanations.
Yeah, that model runs into some big problems. For one, it doesn't do a good job of separating, just re-describing a phenomenon, using a general law, from really explaining it by showing you the mechanism behind it. And then there's the issue of relevance. How do you decide what factors actually matter for a good explanation? The CL model doesn't have a great answer for that. It also struggles with the idea that explanations can be more or less complete depending on the context, how much detail you need. And finally, whether a CL explanation makes sense, that depends only on the logical link between the thing explaining and the thing being explained. It doesn't matter if it helps you understand the actual causal structure of the phenomena.
So philosophers started looking for a new framework, something that could do a better job of capturing those important aspects of constitutive mechanistic explanations. And that's where we get the idea of purely phenomenal models.
Yeah, those are models that describe the inputs and outputs of a system, but they don't tell you anything about the internal workings. It's like a black box. They can be useful for describing what a system does, but they're not going to explain how it does it at the level of the actual mechanism.
So how do we go from a purely phenomenal description to a genuine constitutive explanation? The entry talks about this idea of model to mechanism mapping. They call it the 3M requirement.
Right. Kaplan and Craver, they came up with that. Basically, what they're saying is that the variables in your model and the relationships between them, those should line up in a meaningful way with the parts, activities, and causal connections in the real mechanism you're trying to understand.
So it's about drawing those clear connections between what's in your model and the actual reality of the mechanism.
Exactly. But the entry makes a point of clarifying that 3M doesn't mean your model has to capture every tiny detail of the mechanism. It doesn't mean more detail always equals a better explanation.
It just means it needs to accurately represent some of those causally relevant aspects.
Exactly. And it's totally fine to use idealized and abstract models, simplify things to highlight the really important features.
Another big piece of constitutive explanation is this idea of explanatory relevance. How do you decide what actually matters? Which of the many parts and activities in a complex mechanism are actually relevant to the phenomenon you're trying to explain?
Ah, that's a tough one. Can you just go with your gut feeling about what's relevant, causally? The entry brings up some pretty serious conceptual problems with that,
Yeah.
especially when you're dealing with causation across different levels in a mechanism. The problem is the parts and the whole they make up. They're not always independent in the way we usually think about cause and effect. And they often change at the same time, so it can be hard to say which one comes first, which one is causing the other.
So, if relying on our intuitive sense of causation across levels is problematic, how do we figure out what's constitutively relevant?
The entry lays out a few different approaches that philosophers have come up with. One of the big ones is mutual manipulability, or MM. The idea is that a component is relevant to a phenomenon if, when you mess with that component, the phenomenon changes, and when you mess with the phenomenon, the component changes. You can intervene on either side and get a result. But MM has its critics. Some people think it implies too direct a connection between levels, which they find problematic. Plus, it doesn't always match up with our intuitive judgments about which parts are really crucial for a mechanism to work.
There's also the regularity account, which uses Mackey's famous I knew S condition. In that view, a relevant component is something that's not enough on its own to cause the phenomenon, but it's a necessary part of a set of conditions that are sufficient. It's not redundant, it plays a unique role. And then there's the fat-handed intervention approach, which argues that if you try to intervene on the whole mechanism, you'll inevitably affect lots of its parts at the same time, suggesting this really tight coupling between the phenomenon and its components.
And all these different approaches just show how much debate there is about the best way to understand constitutive relevance. It's a reminder to be really careful about the epistemology, the metaphysics, and the practical side of scientific reasoning.
The entry then moves on to these norms of completeness and correctness when it comes to mechanistic explanations.
Right, so how complete does a mechanistic explanation need to be? The entry emphasizes that our models are always going to be simplifications. You can't include every single detail. How much detail you need depends on what you're trying to achieve and the context you're working in. Glennon, he says there's no hard and fast rule. We're always refining and expanding our models of mechanisms. Craver and Kaplan, they talk about salmon completeness, where the gold standard is the mechanism itself in all its messy complexity. But they also acknowledge that even incomplete models can be really useful and explanatory.
And how do you figure out if your explanation is actually correct? Does it accurately represent how the phenomenon is produced?
Well, a lot of mechanists distinguish between how possibly schemas, which basically describe a plausible way something could happen, and how actually enough schemas, which describe how it actually does happen, with enough accuracy for the situation. How much accuracy you need can vary, of course. And it's important to remember that idealized models, even if they're not perfectly true, can still give you correct and important information about the key features and causal relationships in a mechanism. A lot of contemporary mechanists, they're leaning towards some kind of perspectival realism, acknowledging that our understanding is always shaped by our perspective and interests, but it's also grounded in the objective reality of the mechanism.
The entry wraps up this section on the importance of mechanistic explanation by talking about intelligibility. How do these mechanistic models actually help us understand the world better?
The big thing they provide is what you could call a mechanistic model. It's like a blueprint that shows you the relevant parts, the activities they're doing, and how those interactions are organized to make the phenomenon happen. These models often present a step-by-step sequence. They show how complex behavior can come from simpler changes at the level of the parts, and they often give you a kind of functional or teleological view by highlighting the roles of different parts. And they often show you the spatial arrangement that enables the whole thing to work. It's like a story, a causal narrative, that helps you see how it all unfolds.
But it's not just those strictly mechanistic models, narrowly defined, that contribute to our understanding, right?
No way. You can have models that don't perfectly fit that definition. Things like dynamical systems models, network models, minimal models that just focus on the essentials, or representations of causal pathways. They can all give you different pieces of the puzzle.
So you might have a model that highlights the evolution of the mechanism over time, its overall structure, the basic rules it operates under, or all the different factors that might be influencing it.
Right. And often, the best understanding comes from combining insights from multiple models, even if they have different assumptions or seem to be telling you slightly different things.
Really makes you appreciate how complex this all is.
It is.
Okay, so we've established what mechanisms are, why they're so important, and now the entry gets into the nitty-gritty of how scientists actually discover them.
This is where the rubber meets the road, right?
Yeah.
The theory connecting to actual scientific practice. The concept of mechanism. It's a powerful way to think about how scientists figure things out. It's a different approach from those more formal computational methods of causal discovery. A mechanism, its material structure and organization, those give scientists real, concrete clues to follow.
The entry highlights Bechtel and Richardson's work. They outline this general process of discovery. First, you got to characterize the phenomenon. What exactly are you trying to explain? Then you try to pinpoint where in the system the mechanism for that phenomenon is located. And then you got to break down the mechanism into its parts and figure out what each one does.
In Darden, she emphasizes that discovering mechanisms is usually an iterative process. You're constantly building schemas, testing them against the evidence, and then revising them based on what you find. She points out different strategies that scientists use, like borrowing schemas from other areas, building complex mechanisms from simpler ones, and using both forward and backward reasoning to figure out how it all works. They even talk about using robotic simulations to test ideas about how a mechanism might operate.
And for evaluation, the entry talks about constraint-based reasoning. So checking whether a mechanism fits with what we already know. And then, of course, there are experiments. Inhibitory experiments where you block something, stimulatory experiments where you activate something, and activation studies. All designed to test specific ideas about the roles of different components.
This focus on those concrete, hands-on strategies is a big contrast to those super abstract approaches to scientific discovery.
And the entry also points out that we need to do more work to connect these more heuristic accounts of mechanism discovery with those increasingly sophisticated formal methods of causal inference.
Definitely.
There's also a section specifically on the role of mechanistic evidence in medical discoveries, especially compared to statistical evidence. That seems like a really important area for putting all this into practice.
Huge implications there. It's this ongoing debate about the importance and reliability of statistical correlations, which show you a relationship between things, versus evidence that actually explains the mechanism. The Russo-Williamson thesis, for example, argues that you usually need both kinds of evidence to make a strong causal claim, especially in medicine.
Yeah, you need that mechanistic evidence to show how a cause produces its effect. That makes the statistical evidence more believable, less likely to be just a fluke.
Right. And this view challenges that traditional hierarchy of evidence you find in medicine, where they put randomized controlled trials at the top. The mechanistic perspective says you got to take a more integrated approach. Value both statistical and mechanistic evidence when you're assessing causal claims. The entry also mentions Steele's work on comparative process tracing. That's a cool strategy for taking what we know about mechanisms from well-studied model systems and applying it to real-world situations that are harder to study directly.
All of this leads us to, the ultimate philosophical question, right? Are mechanisms real? Are they objective features of the world that we're uncovering, or are they just useful tools that we've invented?
This is where the metaphysics gets real, so to speak. Mechanists, they have a range of views on this, but a lot of them lean towards what's called perspectival realism. It's kind of middle ground.
So how does that work?
Well, the perspectival part comes from the fact that mechanisms are always mechanisms of a specific phenomenon. And as scientists, as humans, our interests are going to influence which phenomena we choose to study, how we frame our questions. Even the way we divide a mechanism into its parts, that's often influenced by what's relevant to our goals, what makes the mechanism understandable to us. Even when you're describing the function of a part, there's a bit of perspective there, because you're describing its role in a larger system, and that role is defined by how the whole system behaves, which we're interested in.
But it's not like we just pick phenomena to study at random, right?
Right.
And the way we break down mechanisms, that's got to be guided by how things are actually causally connected in the world.
Of course. Like, If a system is nearly decomposable, that might give you a natural way to chunk it into parts. And functional descriptions, if they're going to be accurate, they have to reflect the actual contribution a part makes to the whole mechanism. So there are these objective constraints. It's not just all in our heads.
So we've got this interplay between perspective and objective reality.
Exactly. And there's some good debate going on among mechanists about how much weight to give to each side. Some emphasize our cognitive abilities and our need for explanations as the main drivers of how we understand mechanisms, while others say it's more about those stable, independent causal structures that exist out there.
And finally, our deep dive looks at how different scientific disciplines are connected through this lens of mechanism. This is really key for thinking about the unity and the diversity of science.
Yeah. Historically, mechanism and reductionism went hand in hand. The idea was that you could explain everything at higher levels by breaking it down to its lower-level components. But nowadays, mechanistic thinking often aligns more with anti-reductionism and the importance of explanations that span multiple levels. Mechanisms themselves, they often cross those levels, and to understand a phenomenon fully, you need to see how mechanisms work and interact across those different levels.
The mechanistic framework offers an alternative to that old covering law model of reduction. It focuses on the relationships between parts and activities within a mechanism instead of trying to derive higher-level laws from lower-level ones. And it supports the idea that there can be real, higher-level causes that aren't just reducible to the interactions of lower-level things.
When it comes to ontological reduction, the question of whether higher-level entities are really just collections of lower-level stuff mechanists often argue that the way those lower-level parts are organized can create genuinely new emergent phenomena at the higher level, things you can't fully grasp just by looking at the parts in isolation.
Yeah, the relationship between mechanism, reduction, and emergence is a tricky one. Mechanists talk about different kinds of emergence, like mechanistic emergence, which is about organization, epistemic emergence, which is about our limited knowledge, and then those more like metaphysically spooky versions of emergence. And there's the concept of mechanistic realization, which helps us understand how different levels are connected in a mechanism.
And instead of picturing science as this unified thing where all theories ultimately get reduced down to one fundamental level, the mechanistic perspective often leads to a view called interfield integration.